Now we'll implement a current controlled voltage source using an op-amp which is modeled as a voltage controlled voltage source. A current controlled voltage source obeys the relationship output voltage V0 equals the input current II times some resistance Rm, which is the trans resistance or trans impedance of the current controlled voltage source. Okay. Just like in the case of the current controlled voltage source using a MOS transistor, we define an error voltage V0 minus IIRM, and if this happens to be more than 0, it means that the output voltage is higher than what is desired. The output must be reduced. And similarly, if this is less than 0, output must be increased. Okay. Now, if you consider an op-amp which we model as a voltage controlled voltage source, there is the input difference voltage Vd and the output is some A0 times Vd, and A0 is a large number, or you would like it to be a large number. Now, how does this work? If Vd is positive, the output will be driven to a large positive value. If Vd is negative, it will be driven to large negative value. Okay. So that means that to reduce the output voltage, you have to make Vd more negative. Okay. That is, we have to reduce Vd, or we have to make it more negative than what it currently is. And similarly, to increase the output, Vd must be made more positive. Okay. Now here you see that if the error voltage V0 minus IIRM is less than 0, the output must be increased. Okay. So putting the two together, you see that when V0 minus IIRM is less than 0, Vd must actually be greater than 0. Okay, Vd is the input difference voltage of the op-amp with the signs defined like this. Okay. So if this is the output voltage and this is Vd, I would like Vd to be minus V0 minus IIRM, so that the actions described here can happen. Okay. If Vd equals V0 minus IIRM, what happens is that when Vd is less than 0, the output will be further reduced to negative values. Okay. So that's not what you want. So Vd has to be equal to minus V0 minus IIRM. Now, how do we obtain this V0 minus IIRM? Just like we did in the case of the transistor current control voltage source. If this is the output node and this is the input current source, then if I connect Rm like that, the voltage here will be V0 minus IIRM. Okay. And we want that to be equal to minus Vd. So convenient way to do that is you connect this to ground and connect it here. So now you can see that minus Vd equals V0 minus II times Rm. Okay. So a current controlled voltage source using an op-amp, it looks like this. Okay, so this is V0, this is Rm, and this is II. Okay. Of course, the input source can have an internal resistance Rs. Okay. Now, the op-amp is modeled as a voltage controlled voltage source. That means that if this voltage is Vd, the output voltage V0 is A0 times Vd. Okay. Let's analyze what exactly we get from this, and for simplicity, I will not include RS, but you can include it and analyze it and see what you get out of it. In this case, we know that this VD here, this voltage has to be V0 minus II Rm. Okay, because this current has to flow into the resistor. Nothing goes into the op amp. We assume that the input resistance of the op amp itself is infinite. So now this is equal to minus Vd, and from this we can see that Vd equals V0 by A0, which is V0 by A0. Okay. From this we see that V0 by II equals Rm divided by 1 plus 1 by A0. Now this is the desired ratio between the output voltage and the input current, and we have something extra in the denominator, but the denominator reduces to unity, and this ratio goes to Rm if A0 tends to infinity. Okay. If the gain of the op amp is infinite, then we get exactly what we want. Okay. So this is the current controlled voltage source using an op amp. Now, just like in many other current control devices, many times such a device is used actually with a voltage input. That is, imagine that we had a current controlled voltage source Rm, and this is the source resistance Rs. We can convert the parallel combination into a series combination of Rs and a voltage which is minus II Rs. Okay, and this drives current controlled voltage source. Okay. Now once we have this circuit, we can forget that we ever started from a current source. We can just think of this as a voltage source Vi. Okay, and draw it like this, where we have some resistance Rs in series with the input source. Okay, now we can forget about the fact that this was the internal resistance of the current source. We have some voltage source and we have some resistance here in series, and we have some resistance Rm over there. Okay, the output voltage here is II times Rm, which can also be written as minus Vi Rm by Rs. Okay, so if this is V0, V0 by Vi will be minus Rm by Rs. Okay. Now, of course, usually these are not denoted Rm and Rs if you are not using them as a trans impedance amplifier. You just call them R1 and R2. In that case, they become minus R2 by R1. Okay. So this is nothing but a current controlled voltage source driven by a series combination of voltage source and a resistor. Okay, many times it's used like that. In this case, you do see that the gain depends on Rs, which is in series with the voltage source. Okay, this is not a voltage controlled voltage source, because in a voltage controlled voltage source, the gain V0 by Vi should not depend on the internal resistance of Vi. Now, for instance, if there is another resistance here that appears in series with this, and the gain will depend on that resistance. Okay, so this is a current controlled voltage source driven by a voltage source in series with its internal resistance. Okay, so now we have seen two circuits: voltage controlled voltage source using an op amp, which looks like this, and a current controlled voltage source using an op amp, which looks like that, And in case of voltage controlled voltage source, the output will be exactly K times Vi, where this K is given by the resistor ratio. If this is K minus 1 R and R, K is what appears there. Okay. Or if you call these R2 and R1, this will be 1 plus R2 by R1 times Vi. Okay. And in this case, the output voltage will be IIRM. Now, these are true if the gain of the op amp goes to infinity. Okay. So, an op amp whose gain is infinity, it's known as an ideal op amp. Okay. And in case of an ideal op amp, the gain of this will be 1 plus R2 by R1. The gain of this will be Rm. Okay. And a variant of this, which can be driven with a voltage source, is Vi R1 R2. Okay. Here the output will be minus R2 by R1 times Vi if the gain of the op amp is infinite. Okay. Now, of course, these two circuits are very likely very familiar to you, and they are nothing but the classic non-inverting amplifier and the inverting amplifier. Okay. So that's how we can realize control sources using an op amp as well. So we can also realize control sources using an op amp. We have seen how to make a voltage controlled voltage source as well as a current controlled voltage source. Okay.